Well, in this class what we are going to do, we are going to analyze a system where we are going to have a electric field enhanced GLR controlled filtration in a tube, and we have done a corresponding part. If you remember, in case of laminar in earlier without electric field, whenever there was a flow through a rectangular channel. So, in order to get a the difference between that analysis and this analysis, what I have decided to carry on an analysis in a tube, number 1. Number 2, we are going to have a turbulent flow instead of a laminar flow, and see how the analysis will be different in this particular case. It is a GLR controlling ultrafiltration and it is being assisted by external electric field. So, the problem that we are going to solve is electric field assisted GLR controlled ultrafiltration in a tube. Okay. So, this is a tube, this is the length of the tube and this is the radial location, and you are going to have the there is a build up and there is a permeation from the wall uniformly from all the surfaces, and there is a development of mass transfer boundary layer on the wall. Okay. So, basically what we are going, so here it is C is equal to C naught, and you will be having C naught up to C gel on the membrane surface. Okay. So, within the mass transfer boundary layer. So, what we, if you remember what we have done in the earlier analysis, we did a solute balance in concentration boundary layer or mass transfer boundary layer under the steady state. This is a steady state operation. So, solute balance in mass transfer boundary layer what it will give is the, if you write down in radial coordinate, it becomes u del c del x plus v plus v e del c del r is equal to d by r del r of r del c del r. Okay. It should be basically v. Okay. What is this v? So, if this is u and v at the velocity component respectively in the x and y direction, x and r direction. In this case, y direction is nothing but the r direction. Now, the velocity will be having two components. One will be the electrophoretic velocity, another will be it's basically relative velocity. Okay. Now, the electrophoretic velocity can be related to the electrophoretic mobility. V e will be and this becomes u e times e where u e is nothing but electrophoretic mobility and E is the electric field strength. How you got the external electric field in this particular case? Because you are going to have the membrane on the surface of the tube. So, that will be one electrode. Where is the other electrode? So, it will be something like this. This is the wall, and in the central line you insert a plate or a tube of titanium. Now, connect the external voltage supply via this. Okay. So, in the middle of the here in the middle plate it is basically one electrode and the body of the setup or the cell is another electrode. These two electrodes are connected by the external power supply, voltage power supply. Then it will create an external, it will create an electric field between the wall and the center line. Yeah, that is how the electric field will be generated in this particular setup, unlike the rectangular plate. Okay. In a rectangular coordinate system, if it is a flow through a rectangular channel, it is very easy to identify the electrodes, the top plate and the bottom plate, you can connect it to the external power supply. But in this particular case, you have to insert a special, you have to do a special arrangement by inserting a titanium rod or electrode in the middle of the whole setup tube. Okay. Now, if you remember, we are talking about the separation of a protein. So, protein diffusivity will be in the order of 10 to the power minus 11 meter square per second. Okay. So, you are talking about a Schmidt number mu by rho d, mu is 10 to the power minus 3, rho is 10 cube. So, 10 to the power minus 6 and it is 10 to the minus 11. So, it will be 10 to the power 5. Okay. So, we are talking about very high Schmidt number, and we have already seen earlier that thickness of mass transfer boundary layer is inversely proportional to Schmidt number. So, the mass transfer boundary layer thickness or concentration boundary layer thickness will be extremely small. That means, in the tube the generation of the mass transfer boundary layer will be extremely small compared to the radius of the tube. Now, our concentration is varying within that thin boundary layer, not outside. Outside is C is equal to C naught. So, therefore, since the boundary layer thickness is pretty small, we can neglect the curvature effect. The same way we have, I was explaining in the yesterday's class that if you stand in front of a big sphere, it will lose its curvature effect. It will be, you will be observing it as a flat plate. So, therefore, you need not to consider this geometry as a radial polar coordinate system. It will be simply a rectangular polar coordinate system in this particular case. So, if you you can set up your y coordinate from the at the wall and it goes into the center, and the x coordinate is as before. So, under this condition, the solute mass balance equation in radial polar coordinate system will boil down to the rectangular coordinate system. So, this becomes u del c del x plus v plus v e del c del y is equal to d del square c del y square, where y is the coordinate system away from the wall. Okay. Now, we assume a turbulent flow. Previously, we assumed a laminar flow, but in this case we are assuming a turbulent flow analysis. Now, in this case, as we have discussed earlier, the thickness of mass transfer boundary layer delta is extremely small. So, therefore, if you remember that if you consider about a fully developed turbulent velocity profile, the fully developed turbulent velocity profile will be having, the profile will be something like this. Okay. There will be a thin region that is known as viscous sublayer. Then you will be having a transition region. Then you will be having a turbulent core. Now, since we are talking about a flow of high Schmidt number, the delta will be very small. That means, delta will be within the delta, there is every possibility that delta will be lying within the viscous sublayer. Okay. And the viscous sublayer, the viscous forces will be dominant. Okay. The viscous forces will be dominant. And if you remember, the velocity profile was, it looks like u plus is equal to y plus for y plus lying between 0 and 5 is equal to some constant 2.5 ln y plus another constant, let us say 4, that is for y plus lying between 5 and 20, and there will be another constant, let us say C1 ln y plus another constant C2 for y plus greater than 20 or 25, 30, right? It is greater than 30. That means there is a particular profile, and this profile is linear within the viscous sublayer. U plus is equal to y plus, all these are non-dimensional, I will come to that those non-dimensional term. U plus is equal to y plus, that is for y plus 0 to 5 from the wall to a particular distance, that is the viscous sublayer, it is linear there, and here it is 2.5 ln y plus 4, and beyond that it is a turbulent core. Okay. Now, if we assume that our mass transfer boundary layer lies within the viscous sublayer of this fully developed turbulent velocity profile, then I will be talking about only the linear part of the velocity profile. That means I am talking about u plus is equal to y plus. I need not to bother about the other two parts, because the concentration difference is nothing there, it is C is equal to C naught everywhere. So, and these will occur only because we are talking about high Schmidt number solute. High Schmidt number solute means very small diffusivity. Since and the typical solutions are filtration particles that we are talking about are proteins, colloids, things like that, which will be having pretty low diffusivity. So, therefore, we are going to have very high Schmidt number and thickness will be pretty small, and we assume in this particular analysis that it lies well within the viscous viscous sublayer. If we do not assume that, obviously it may not be there, right, but we cannot do it analytically in the class. It has, you have to go for the numerical methods for that. So, our assumption is thickness of mass transfer boundary layer is such that it lies well within the viscous sublayer of turbulent velocity profile. So, what is the velocity profile? U plus is equal to y plus. Now, let us come to the different conditions, etc. What is u plus? Non-dimensional term, u plus is equal to u by u star, and what is u star? U star is known as the friction velocity. Okay. And this is nothing but under root tau w by rho. What is tau w? Tau w is the wall shear stress, and rho is the density of solution or the medium. Okay. And what is y plus? Y plus is again non-dimensional distance, it is y u star by nu. Okay, that is the nu. What is nu? Nu is the kinematic viscosity mu by rho. So, mu is the density, mu is the viscosity, rho is the density. So, it is known as the kinematic viscosity. Okay. And this relationship is valid for y plus lying between 0 and 5. Okay. Next, we look into the correlation of tau w or the wall shear stress. for smooth wall, I think this is known as the fanning friction factor. This tau w becomes given as 0.03325 rho u naught square nu over r u naught raised to the power 0.25. You can look into any standard textbook of fluid flow, you will be getting this expression for the smooth wall or smooth tubed wall, okay, or tube with a smooth wall, and rho is the density, u naught is the cross sectional average velocity. This u naught is the cross sectional average velocity. How we can estimate the u naught or cross sectional average velocity? That we can estimate, that you can measure. You know the flow rate, you put a rotameter, know the flow rate, you know the area of the cross section, and the flow rate divided by area of the cross section will give you the cross sectional average velocity. Cross section of the tube. What is the area of cross section? Pi r square in this particular case. Now, if it is that, now we can the thing within the bracket nu by r u naught is nothing but okay, it is basically nu is nothing but mu by rho. Rho u naught r, you multiply and divide by 2. So, this becomes 2 mu rho u naught d. D is the tube diameter, because it is flow through a tube geometry. So, rho u naught d by mu is nothing but the Reynolds number. So, this is nothing but 2 by Reynolds number, where you define Reynolds number as rho u0 d by mu or u0 d by nu, does not matter. Okay. So, we identify that, and let us get the expression of u as in the form of ky. So, that is our idea. If you do that, then let us define u plus as u by u star and y plus is equal to y u star by nu. Our velocity profile in this particular case was u plus is equal to y plus, right. So, just put the value of u plus, u by u star is equal to y u star by nu. Okay. So, it becomes u is equal to u star square by nu multiplied by y, and if you remember, u star was under root tau w by rho. So, u star square will be tau w by rho. So, it will be tau w by rho times nu multiplied by y, and now you put the expression of tau w that we have written earlier. So, this becomes 1 by rho nu 0.03325 rho u naught square 2 to the power 0.25 Reynolds to the power minus 0.25 times y. Okay, you just put the earlier expression, and what you will be getting is that u is equal to 0.0395 u naught square divided by nu Reynolds raised to the power minus 0.25 times y. This is the velocity profile in the dimensional term, and it is u is equal to k times y. Now, we can write it in the form of u is equal to k times y. Okay. Where k is 0.0395 u naught square divided by nu Reynolds to the power minus 0.25. Okay. And we are assuming the mass transfer boundary layer is really very thin, and velocity component v in the definition of mass transfer boundary layer will be same as that in the wall. Okay. And the wall, it was the permeation velocity. So, V will be approximated by minus J at the wall. So, therefore, your the solute mass balance equation now becomes U del C del x plus V E minus J del C del y is equal to D del square C del y square. That means, your electrophoretic velocity is in the upward direction, J is in the downward in the opposite direction. Okay. So, U del C del x minus J minus V E del C del y is equal to D del square C del y square. If you remember, the governing equation of solute mass balance within the mass transfer boundary layer without any external electric field, if you put the value of V equal to 0, you get back your governing equation when there was no electric field. Okay. Fine. Now, let us look into the boundary conditions. We require to have one boundary condition with respect to x and two boundary conditions with respect to y as earlier. The boundary conditions were at x is equal to 0, c is equal to c naught, at y is equal to delta or at the edge of the boundary layer c is equal to c naught, and at y is equal to 0 d del c del y plus j minus v e c is equal to 0. Okay. So, this boundary condition we have discussed at length, that net flux, net solute flux towards the membrane at the steady state will be equal to 0. This is the diffusive flux away from the membrane, J times C is the convective flux towards the membrane, minus V times C is the diffusive flux away from the membrane due to electrophoresis. Okay. Now, these equations, these boundary conditions will set the full governing equation, the boundary condition of the governing equation. So, now let us non-dimensional the non-dimensional is the governing equation. The governing equation becomes U del C del x minus J minus V E del C del y is equal to D del square C del y square. Now, let us make it non-dimensional by x star as x by L, the length is known, C star as C by C naught, P E E Peclet number because of electric field becomes V d by d, P E W the Peclet number because of the wall suction, that is J d by d, d is the diffusivity and this small d is nothing but the diameter of the tube, and y star is equal to y by r, r is the radius. So, it will be non-dimensional against that number. So, if you really do all this non-dimensional this equation, the final form of the equation becomes, I am writing the final form, you can match it, A y star del C star del x star minus P w minus P e divided by 2 del C star del y star is equal to del square C star del y star square. Okay. And the constant A is 0.0395 divided by 8 Reynolds raised to the power 1.75 Schmidt d by L. Okay. I have omitted number of steps, probably 2 steps. You please express all these quantities in the non-dimensional form and do one step and just try to derive this equation and check whether you are getting the same thing or not. Okay. If you remember, we got the same formula in case of without electric field under the laminar flow condition. In that case, this P E term was not there, it was 0, and this A was 3/16 Reynolds Schmidt d by L. Okay. Fine. Now, the non-dimensional governing equation, you must have the non-dimensional form of boundary conditions. These are at x star is equal to 0, C star is equal to 1, at y star is equal to delta star is at the edge of the boundary layer, that means y by r, delta star is delta by r, C star equal to 1, and at y star is equal to 0, you have del C star del y star plus half PEW minus PEE C star is equal to 0. And since it is a gel layer controlling filtration, at y star is equal to 0, C star is nothing but Cg star. But anyway, that is a physical boundary condition that we will be utilizing later on, but these are the 3 boundary conditions to solve the governing equation of the partial differential equation of concentration within the mass transfer boundary layer. Now, this set of equations, what we are going to do, we are going to use an integral method of solution as earlier. Okay. And it is an approximate method, that means we are going to approximate, we are going to assume a concentration profile within the mass transfer boundary layer. Since the concentration profile you are assuming, it is known as the integral method is known as the approximate method solution. So, we are going to use an integral method of solution. It is an approximate method. Why it is an approximate method? Because you are going to assume a concentration profile. Okay. Now, the concentration profile that we are going to select or we are going to assume is C by C naught is equal to A1 plus A2 y star by del star plus A3 y star by del star square, okay, where delta star is nothing but delta by r. At y star is equal to, now the boundary the conditions this concentration profile must satisfy is that at y star is equal to delta star, C star is equal to 1. So, that is the definition, right. At the edge of the boundary layer, the concentration is 99% of the free stream concentration. So, it will be at y star equal to delta star, C star is equal to 1. At the same time, another boundary condition must be satisfied at the edge of the boundary layer, that is del C star del y star must be equal to 0. These two boundary conditions must be satisfied at the edge of the boundary layer, any type of boundary layer, even if it is a thermal boundary layer. At y star is equal to delta star, thermal boundary layer, T star was equal to 1 and del T star del y star will be equal to 0. Now, since there are 3 constants, you must be having one more boundary condition. The boundary condition that is quite apparent is that at y star is equal to 0, your C star was equal to Cg star. Okay. Now, these 3 are bare minimum concentration, bare minimum conditions you know for this particular concentration profile to satisfy. So, therefore, you must be having 3 unknown constants in your concentration profile. That means, you can go up to a quadratic approximate means profile of the concentration. Now, using these 3 conditions, you can evaluate the constants A1, A2 and A3. Let us do that. At y star is equal to 0 means 0 is equal to A1 plus, okay, y star is equal to 0 means C star is equal to Cg star. So, Cg star is equal to A1. Okay. The next term was equal to 0, next the third term is also equal to 0. So, therefore, C star is equal to Cg star plus A2 y star by del star plus A3 y star by del star square. Now, out of these 3 conditions, you have already utilized this condition. Now, you utilize these 2 conditions. At y star is equal to delta star, C star is equal to 1. That means, 1 is equal to Cg star plus A2 plus A3. Okay. That is condition 1 condition, and the other one is del C star del y star is equal to 0. You take the derivative of this equation and put it equal to 0 at y star equal to delta star. So, since gel layer concentration is constant, so first term derivative of the first term will be equal to 0. So, 0 equal to A2 by del star plus 2 A3 y star by del star square, right. This y star has, the whole thing has to be evaluated at del star. So, that means del star will be cancelling. So, you will be getting A2 by delta star plus 2 A3 by delta star, that will be equal to 0, that is del C star del y star, right. Now, you are going to have the second condition. Now, using these two conditions, you can get the concentration profile. Okay. So, A2 by del star plus 2 A3 by del star, that will be equal to 0. So, A2 is equal to minus 2 A3, okay. And the other one is 1 plus Cg star plus A2 is minus 2 A3. So, 2 A3 plus A3. So, you will be getting A3 is equal to Cg star minus 1 and A2 is equal to minus 2 A3 minus 2 Cg star minus 1. So, the concentration profile you are going to get C star is equal to Cg star minus Cg star minus 1 to y star by del star minus y star square by del star square. This is square here. So, this is the concentration profile that we are going to use in order to solve this equation. Now, what we are going to do? Now, your Cg star is constant, because Cg is constant, and delta star is a function of x only. Now, what we are going to do? We are going to get the derivative of with respect to x, you get the derivatives with respect to y and del square C star del y star square, and substitute this derivative in the governing equation. Okay, that we are going to do. So, del C star del x star will be nothing but minus Cg star minus 1 minus 2 y star by del star square plus 2 y star square by del star cube d del star dx star. This becomes minus 2 Cg star minus 1 minus y star by del star square, just taken 2 out, plus y star square delta star cube d delta star dx star. Okay, that is del C star del x star. Del C star del y star, this becomes minus Cg star minus 1 2 by delta star minus 2y by delta star square. Okay. And del square C star del y star square will be one more derivative of this equation, that means only this term will be there. So, minus minus plus, so it will be Cg star minus 1 2 by delta star square. So, these are various derivative, and that we are going to put in the governing equation. So, if you remember, it was A y star del C star del x star plus P E w minus P E by 2. Okay, it was minus, right, del C star del y star is equal to del square C star del y star square. That was the governing equation most probably. Now, what we are going to do, you just substitute this derivative in terms of y star and delta star in this equation and see what you get. If you substitute all these derivatives here, the final form that you are going to get is that A d delta star dx star y star square divided by delta star square minus y star cube divided by delta star cube plus P E w minus P E e divided by 2. This minus sign will be consumed here inside, 1 by delta star minus y star by delta star square, okay, is equal to 1 over delta star square. So, now what you are going to do, it is a standard boundary layer theory, you multiply both sides by dy star, that is you take the 0th moment, take zeroth moment means you multiplied both sides by y to the power 0 dy, y star to the power 0 dy star, and integrate across the boundary layer thickness 0 to delta star. So, it will be a d delta star dx star 0 to delta star y star square by delta star square minus y star cube divided by delta star cube dy star plus P w minus P e e divided by 2 multiplied by 0 to delta star 1 over delta star minus y star by del star square dy star, and it will be right hand side you will be having delta star square dy star 0 to delta star. Okay. So, once you do that and you just carry out this integration, this becomes y star cube by 3. So, it will be delta star cube. So, delta star cube and delta star square, it will be delta by 3 here, and similarly you will be getting minus delta star by 4. Okay. So, whole thing becomes delta star by 12. Okay. So, you can simplify this thing and can do this analysis, and finally you will be getting the neat form of the integration as a delta square by 12 d delta star dx star plus P w minus P e e divided by 4 times delta star is equal to 1. Okay. So, this is the form you get after y averaging the equation of solute mass balance equation. Now, if you remember the boundary condition you had at y star is equal to 0, it was del c star del y star plus half P w minus P e e times C g star is equal to 0. Now, what we can do, we already got the derivative del c star del y star in terms of delta star and y star, and then evaluate that derivative at y star equal to 0. Okay. If you evaluate the derivative at y star equal to 0, I am just talking about this term del c star del y star evaluated at y star equal to 0, that means this term will be off and you will be getting minus 2 C g star minus 1 divided by delta star. You put that into this equation and what you will be getting is minus 2 by del star C g star minus 1 plus half P w minus P e e, and C star becomes C g star there at y star equal to 0. So, C g star equal to 0. So, you will be getting P w minus P e e divided by 4 times delta star is equal to C g star minus 1 divided by C g star. So, what we are going to do, we are going to substitute this into this equation. Okay. If you are going to, if you really substitute it, what you get is a delta star square divided by 12 d delta star dx star plus C g star minus 1 divided by C g star is equal to 1. So, you take it on the right hand side, you will be getting a delta star square divided by 12 d delta star dx star is equal to 1 minus C g star minus 1 divided by C g star. If you simplify this thing, so C g star will in the numerator will be cancelling out, it will be minus minus plus 1, this becomes simply 1 by C g star. Okay. So, next we separate the variables and see what you get. Delta star square A delta star square by 12 d delta star dx star is equal to 1 over C g star. So, delta star square d delta star is equal to 12 by A C g star and just times dx star, right, from 0 to x star, and this will be from 0 to del star. So, we will be getting an expression of del star, and this becomes del star by 3, delta star cube by 3. So, delta star will be 3 into 12 36 A C g star raised to the power 1 upon 3 x star raised to the power 1 upon 3. So, that is how the delta star or the thickness of mass transfer boundary layer varies as a function of x star or the length in the module. Okay. Now, let us look into the mass transfer coefficient and rest of the calculations. Mass transfer coefficient in this case, if let us look into the definition, k C g minus C naught is equal to minus d del C del y at y is equal to 0. Okay. So, this is the mass transfer coefficient. C is the concentration at the lower surface, minus C naught is the bulk concentration. So, that is by definition. This is by definition. Now, make it non-dimensional. So, you can define the Sherwood number. Okay, you can get k as minus d del C del y at y equal to 0 divided by C g minus C naught. Okay. Define, make it non-dimensional, that means C star by C by C0 is the C star and y star is y by r and things like that. If you do that, k is equal to minus d del C star, there will be a small r here, del y star at y star equal to 0, and this will be C g star minus 1. Okay. So, this will be k r over d minus is equal to minus del C star del y star at y star is equal to 0 divided by C g star minus 1, and our Sherwood number is defined as k d by d. So, that means twice of r. So, it will be minus it will be minus 2 del C star del y star at y star is equal to 0 divided by C g star minus 1. Okay. So, if you put the expression of del C star del y star at y star equal to 0, I think we have already done that earlier. Del C star del y star at y star is equal to 0, you will be getting 2 by delta star multiplied by C g star minus 1 with a negative sign. So, in the definition of Sherwood number, this negative will be positive and the 2 will be coming. So, it will be 4. So, if you substitute that this derivative here, the C g star minus 1 will be cancelled from the numerator and denominator, and you will be getting Sherwood as equal to 4 by delta star. And we have just derived how delta star is varying as a function of x star. Okay, how delta star is varying as a function of x star. If you substitute it there, then you will be obtained that how Sherwood number is varying as a function of x star, and then you can do an averaging, length averaging Sherwood number. Okay. So, if you do that, the Sherwood number turns out to be 4 into A C g star by 36 raised to the power 1 upon 3 x star to the power minus 1 upon 3. You can do a length averaging. Okay. That means, length average Sherwood number will be nothing but Sherwood dx star, x star from 0 to 1. Okay. Let us put the value. So, it becomes 4 and all these things will be constant. 4a Cg star divided by 36 raised to the power 1 upon 3, it becomes x to the power 1 upon minus 1 upon 3 dx star 0 to 1. So, its integration will be minus x to the power minus 1 upon 3 plus 1 divided by 1 by minus 1 upon 3, so 2 by 3. So, you will be getting a value 3 by 2 or 1.5 here, and after integration that will be 1. So, it will be 1.5. After integration the whole integral becomes 1.5, 1.5 into 4 it becomes 6. So, Sherwood number average becomes 6 a Cg star divided by 36 raised to the power 1 upon 3. Okay. Now, you can put the value of A. Okay, we will do that. Now, next we find out what is the length averaged permeate flux. The length averaged permeate flux can be obtained by the definition of mass transfer coefficient and the boundary condition at y equal to 0. It is K Cg minus C naught is equal to minus d del C del y at y is equal to 0, and this is equal to J minus VE times Cg. Okay. Now, what is this? The first equation is nothing but the definition of mass transfer coefficient. If you remember, we just did it right away. Definition of mass transfer coefficient. And what is the last two terms? If you remember, J minus V times Cg is equal to minus d del C del y at y equal to 0. That was the boundary condition at y equal to 0, right. This is the boundary condition at y equal to 0. So, if you equate k times Cg minus C naught is equal to J minus V times Cg, then we will be getting an estimation of the permeate flux. So, you will be getting k Cg minus C naught is equal to J times V Cg, make it non-dimensional, that means k Cg star minus 1 is equal to J minus V times Cg star, that means divided by C naught, and then multiplied by k d by d, you multiply by diameter divided by the diffusivity on both sides, you will be getting Cg star minus 1 is equal to J d by d minus V e d by d times Cg star. So, what is this? This is nothing but the Sherwood number. Sherwood Cg star minus 1 is equal to, what is this? This is nothing but the PW minus, this will be PE times Cg star. So, PW is nothing but PEE plus Sherwood average Sherwood, okay, multiplied by Cg star minus 1 divided by Cg star. Okay. Now, if you do a length averaging, okay, if you do a length averaging, how you do a length averaging? Length averaging means you multiply both sides by dx star and integrate over the dx. So, it is basically integral PW dx star is equal to PEE dx star integration plus Cg star minus 1 divided by Cg star, that is constant. So, this becomes Sherwood dx star integral. Now, 0 to 1, 0 to 1, 0 to 1. So, PW dx star will be nothing but length averaged permeate flux. Now, PE is constant, it does not depend on x star. So, it will be out of the integral. So, integral of dx star is equal to 1. So, this becomes PEE plus Cg star minus 1 divided by C g star, and this integral 0 to 1 S h dx star is nothing but the length average Sherwood number. Okay. So, this is the relationship of the permeate flux, length average permeate flux and length average Sherwood number. So, now we put the value of expression of Sherwood number. This length average permeate flux becomes PEE plus 6 A C g star divided by 36 raised to the power 1 upon 3 C g star minus 1 divided by C g star. Now, we insert the value of A. Insert the expression of A. If you really do that, finally you will be getting, do that I just omitted a single step. This becomes PEE plus 0.32 Reynolds raised to the power 0.58 Schmidt d by L raised to the power 1 upon 3 C g star minus 1 divided by C g star raised to the power 2 by 3. Okay. And the length average Sherwood number turns out to be 0.32 Reynolds to the power 0.58 Schmidt d by L raised to the power 1 upon 3. So, this is the expression of length average Sherwood number in the turbulent flow case, and then we can go for the further simplification. The PEW bar length average flux becomes PEE plus 0.32 Reynolds raised to the power 0.58 Schmidt d by L raised to the power 1 upon 3 C g star to the power 1 upon 3 minus C g star to the power minus 2 by 3. Now, this is the expression that we really want. If you know the Reynolds number, you know the electric field, this is the electrophoretic velocity, non-dimensional term, other properties are known, you can find the permeate flux, but this can further be simplified. For the limiting case, we have discussed this thing. If C g star is much less than e to the power 3, that is 20, this boils down to this expression PEE plus 0.32 Reynolds to the power 0.58 Schmidt d by L raised to the power 1 upon 3 ln C g star. This quantity becomes ln C g by C naught if C g star is less than 20, that we have already discussed in our earlier case when we talked about the laminar flow, gel layer control ultrafiltration and the integral method of solution. Okay. So, this exercise gives a fairly good idea how to apply the external electric field in gel controlling filtration in a tube. So, in this exercise you know how to evaluate the Sherwood number also in case of a tubular geometry under the laminar flow under the turbulent flow conditions. Okay. So, we stop here and we go to the next topic in the next class. Thank you very much.